Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to the SQL Server Instance Module 10 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good overview of the Linux operating system. Let's talk about how to set the SQL Server instance up properly for virtualized SQL Server workloads. In this module, we're going to cover a lot of the SQL Server instance level specifics to help you tune your SQL Server to best fit your virtual machine. We're going to talk about the various options around installation for your instance, max degree of parallelism and cost threshold of parallelism, memory management, and then maintenance tasks. All of these items are designed to boost performance and increase standardization across your deployments. I get asked by a lot of organizations all the time around whether it's a good idea or not to install multiple instances on the same SQL Server OSE. My sarcastic standard DBA response is that it all depends. Realistically, unless our licenses require it, installing just one instance per virtual machine makes our lives easier. If we have just one SQL Server instance to worry about, we can better deal with the resource consumption management at the virtual machine layer with a little bit of involvement inside the operating system. If we have multiple instances installed, we not only have to deal with resource management between all the virtual machines on the host, but now we have to make sure that each instance inside the OSE does not step on the toes of another instance. Tasks like CPU management, available memory for the operating system, job staggering, and maintenance windows all make lives more interesting when we have to deal with these tasks at least two different layers. Having just one instance to worry about means that we can probably deploy smaller virtual machines. I'd much rather have smaller, more atomic units of work to manage. Smaller virtual machines are also easier for hypervisors to time slice and coordinate symmetrical multiprocessing for CPUs. They're smaller to vMotion and smaller to back up. In larger environments, getting operating system level downtime for routine tasks like patching and reboots is a real challenge. The more instances that we have on the same OSE, the harder it is to find a window of time that works best for all application owners to perform routine maintenance. I see this in so many places. Application A can only be taken offline Friday evening starting at midnight for no more than 2 hours. Application B can only be taken offline Sunday morning between 5 and 7 a.m. If these two application databases are in multiple instances but on the same OE, OS level maintenance might just never happen. This is a real problem when the security auditors come around to verify that all of your patches have been applied. Another challenge is when an application vendor requires or demands a certain level of security access that gives them full permissions to the operating system. If that happens, they can see all the files for the other database instance. Many security practices at organizations large and small would prohibit this act, and this requires independent virtual machines to lock the security down even further. If we're leveraging a SQL Server high availability solution that requires the use of Windows Server failover clusters, our availability of all of the instances could be compromised if a glitch takes down the failover cluster layer. I generally like to keep these as atomic as possible, whenever possible. On the flip side, multiple instances on the same virtual machine that we potentially have less OS and SQL Server licenses to worry about. When budget really matters, multiple instances on the same operating system can provide you with a smaller license footprint, provided that the resource consumption of each instance is not that high. Weigh these options carefully as you deploy your SQL servers. Another topic that I get into a lot of discussions around is how to distribute your SQL Server objects. Distribution of these objects start at the virtual machine design and works all the way into the way a single database can be distributed to multiple virtual disks and managed. Like we talked about in the virtual machine design module, I want the most appropriate number of storage controllers, so I have the highest number of storage queues. In this example, we have 4 pvSCSI controllers to maximize our storage access potential. I want multiple virtual disks, so I have better isolation and distribution of the workloads. You always have a C drive for our operating system to boot from. I tend to install my SQL Server instance to a separate small drive. If I need to take a snapshot of my operating system to give me a rollback point for a patch that may act squirrely, I can set my SQL Server disks to what's called snapshot independent so that I can revert the operating system disk back but not lose any of the changes to my SQL Server disks. If I'm doing anything that aggressively uses the system databases, such as transactional replication or availability groups, I may elect to put my system databases on a separate virtual disk. This allows me the flexibility of moving them to a faster underlying storage subsystem if the demand allows. I'll then create one or more disks for my SQL Server database data files and one or more disks for my SQL Server transaction log files. Manage your SQL Server database workload and scale out the number of disks when appropriate. You'll notice that when the storage latency starts to increase under high demand, this is the primary indicator that you may need to start to scale out. For my temp drive, if my tempdb utilization is rather low, you should be able to fit everything on one virtual disk. If my tempdb utilization is very aggressive though, feel free to create more than one virtual disk and spread out your tempdb objects. If you're writing your SQL Server database backups to a local drive, make sure to create at least one extra local drive. Use your perfmon data to understand which of your databases and disks are active at certain periods of the day. You might find that the workloads are very active on competing disks, so you might find that spreading out those disks onto different disk controllers can help you improve storage level queuing inside the hypervisor. Just whatever you do, standardize your deployment so that you know exactly how each machine started. You may have deviations from your deployment standards for larger or more unique virtual machines, but if you start with a common base, any exception to your deployment standards can be documented so you know what to expect. The wide distribution of data like this might seem like overkill. Trust me, it's not. When we get to the performance module, you're going to see some queuing metrics inside the virtual machine layer that give us very clear indications when and where the storage level queuing is occurring inside the hypervisor. From the perspective of minimizing your security footprint and risk per SQL Server instance, I love to use specific SQL Server service accounts, usually one per instance, so that I have a way to define the minimum level of permissions that instance needs to do its job. The number of security breaches that we have personally witnessed over the last few years have been disgustingly bad. I do everything I can to minimize the security risk for any of our servers, but also, if this machine gets compromised, to limit the damage it can do to everything else. Keep in mind there is a newer construct called a managed service account that can continuously change the passwords without taking anything down. I highly encourage you to explore these to see if your environment is able to use them appropriately. Setting the service account also gives us the ability to use some features for performance gains that we can set at the local machine that we'll talk about next. If you're using a domain-based service account or managed service account, we can enable a SQL Server performance feature called instant file initialization. Have you ever performed a database restore and noticed that before the percent counter even hits 5%, it just sits there for quite some time? The database engine has a function that makes sure nothing is on the underlying operating system's disk that may pollute our files. It writes zeros over the database data and log files before these blocks can be used by the database engine. For most environments, these are clean systems that have never had anything other than our SQL Server data on the file system. We can disable the zeroing operation for our database data files by setting a feature in the local security policy for our service account called instant file initialization. What we do is open the local security policy, expand local policy, and then user rights assignment. Find the option called Perform Volume Maintenance Tasks and add your service account here. Restart your SQL Server instance to allow this feature to take effect. One thing to note is that this only works for data files. Log files will always be zeroed out. This is part of the reason why I don't like to set my log growth options to be some crazy high value if the log file needs to grow. I don't want it too small, as it might create VLF segmentation, but I want it to be an appropriate size given the demand on the machine and the speed of my underlying storage to be able to write that stream of zeros while that transaction is held. SQL Server 2016 and above now allow you to set this option during the SQL Server installation process. It's a simple checkbox that says Grant Perform Volume Maintenance Task Privilege during the installer. More details are found at the link on the screen. Now let's go through some instance level defaults. When the SQL Server instance is installed, verify that you have your database default location set. I know this seems like this is something we would do at any SQL Server installation, and you're right. But you'd be amazed at the number of times I find large databases on the C drive when they shouldn't be. It just makes it easier as a default landing location if someone adds a database without asking you first. Your instance configuration has a maximum number of worker threads assigned to it that is configured automatically at instance startup by the number of CPUs present on the server. As part of routine health checks, I want to make sure that our current worker count is not at or exceeding the maximum number of workers. On very active machines or servers inside availability groups, you might find that this number does start to encroach on your maximum worker count value. If this is the case, you might need to adjust the maximum worker thread count at the instance level. Be extremely careful in micromanaging this value. Most of the time, the SQL Server instance does a great job setting this, and if you find you need more, you probably need more CPU as well. Another instance level setting that I make a blanket rule to set is to enable the Optimize for Ad Hoc Workload setting under the Instance Advanced Properties. You'll find that I make very few blanket "you must do this" rules. This setting is one where I have yet to find a reason to leave it disabled. If you have a high number of ad hoc queries, the SQL Server engine might treat them as ad hoc and not reuse execution plans in the plan cache. However, the plans that are still there from previous executions just sit in the plan cache and start to grow their footprint over time. Enabling this setting tells the database engine that the first time it sees a query to compile the execution plan to run the query, and then calculate a hash value from the execution plan. If a list of these hashes does not include the new query hash, keep the hash but kick out the execution plan and release the memory. The next time this query were to run, it would then and only then store the execution plan. It doesn't sound like a lot, but every little bit helps. I find that anywhere from a few hundred megabytes all the way up to tens of gigabytes of the buffer pool memory can be saved by enabling this setting. We spent a high amount of time in the SQL Server Virtual Machine Construction module talking about how to present and better manage your virtual machine NUMA settings. Make sure to go into the instance level properties under processors and verify that your SQL Server NUMA presentation is what you expect. You can also select star from sys.dmos nodes to verify. Where do I begin on this one? If you do a Google or Bing search for the SQL Server settings of cost threshold of parallelism and max degree of parallelism, you'll find a crazy number of threads, all of which usually end up in a shouting match. We have literally spent hours in this course talking about our CPUs and the way that they're properly presented to the virtual machine. These two settings are now how we dial in the way the SQL Server instance uses those CPUs. The first of the two settings is the cost threshold of parallelism. Cost threshold of parallelism is an instance level value, and that is what SQL Server compares against when determining if it needs to take a query and run it on a single CPU thread, or if it should go tear it apart and distribute it on more than one CPU. The next setting is the max degree of parallelism. If SQL Server decides that a query needs to go parallel, this is what it compares against to determine the maximum number of CPUs that it can attempt to parallelize this query on. Let's go into detail on how these two settings are used. When SQL Server receives a command, it analyzes it and determines a cost associated with that query. Usually, the more complex it is, the higher the cost. If the value of this cost is lower than the number specified in this setting, SQL Server will pick a single CPU thread to execute the query on. If the value of this cost is greater than the number specified in this setting, SQL Server will then attempt to parallelize the query and leverage up to the number of CPUs specified in the max degree of parallelism setting to execute those queries on. The default value for the cost threshold of parallelism is a value of 5. This value has been a default in the SQL Server instance since the 1990s. I'm not here to tell you that the default value is wrong or incorrect or antiquated. I am here to tell you that modern CPUs are exponentially faster than those available in the 1990s. What I find is that on many workloads, there's a gray area above the default value of 5 where SQL Server and the CPUs are faster at picking a single CPU thread and running the query than attempting to tear the query apart and parallelize it. It is really difficult to look at a SQL Server and simply guess where this value may land. So anyone's internet-sourced recommendations for default values such as 50 or 100 are most likely wrong for your specific workload. With a little work, we can dial in these numbers for your particular workload. The link on the screen is to a link at a blog post and a query by Jonathan Cahias over at SQL Skills. This link will give you a query that will allow you to collect all the SQL Server execution plans in the execution plan cache and their costs. It will also tell you if they have gone parallel or single-threaded. You will be absolutely amazed. The system in this screenshot is from a SQL Server at a logistics group. The SQL Server had been online for 2 months and contained just 62 commands that had gone parallel. Now take a look at the number of plans in the plan cache that were single-threaded. That 62 went parallel versus over 60,000 that did not. This is actually very normal for relational systems. That's why I don't stress nearly as much about the cost threshold of parallelism and max degree of parallelism than a lot of other people. While important, on a lot of these systems, it doesn't make a huge difference, as a lot of people will advertise. That doesn't mean this default is ideal for your workload. What I love to do to dial in this value is to collect everything that has gone either parallel or single-threaded in that gray area above a value of 5 and below some threshold that you determine. Use Jonathan's query to get the list of statements. If they are non-destructive statements, replay them with the query option max.x and determine for yourself if that particular query runs better in parallel or just single-threaded. What you find might surprise you. You might find that a large number of your SQL Server statements might execute better on just one CPU. In that case, you can start to test increasing your cost threshold of parallelism value. Other times, we may want to limit the impact of these statements. We may elect to turn up the cost threshold of parallelism so that we can keep some things running single-threaded, even if that means it runs longer but consumes less overall CPU. Now, when a query decides to go parallel, the max degree of parallelism setting is what SQL Server looks at to determine the maximum number of CPUs that it can attempt to parallelize that query on. Again, as with any internet research, there are tons of recommendations out there, and most of them are baseless. It's just like the cost threshold of parallelism in that it is completely variable and up to your workload. The default value is 0. Starting in 2017, SQL Server started putting a value of either the number of CPUs on that instance or 8, whichever is lower, into the setup process. The end result is the same, and it just wants to use everything by default. If you have a workload like Microsoft SharePoint, it requires that query parallelism be disabled, and these recommendations are completely irrelevant for those. My general rules of thumb with this particular setting is that if the SQL Server CPU count is small and it is serving up generally relational data, keep the max stop at 0 and test to make sure that an individual statement will not consume all the available CPU. If you find that certain applications just kill the CPU for a long period of time, dial this number back appropriately. If your SQL servers are larger and even contain multiple NUMA nodes, my starting point for testing is to assign the max degree of parallelism equal to the number of CPU cores in one NUMA node. SQL Server is incredibly NUMA aware, and I would like to try to keep a query's worth of activity to a single NUMA node to make sure that it stays fast. Use these as starting points, as they are most certainly not always the endpoint. You could also set the maximum number of cores to 8 if your NUMA node core count exceeds 8. If this is still a physical server, the maximum value should be 16 instead of 8 to accommodate the logical cores. Of course, your environment might be different. As I've mentioned before, it is completely up to your workload and how it's being used. Do the due diligence and test these settings for each of your major servers to make sure they're dialed in properly. Keeping your SQL Server NUMA usage appropriate for your workloads will help you maintain or improve performance. Just so that we can throw one more variable at you, starting in SQL Server 2016, Microsoft decided to implement a feature called automatic soft NUMA. If more than 8 CPU cores exist on a single NUMA node, it looks like SQL Server is less optimal at parallelizing across more than 8 cores. Automatic soft NUMA is when SQL Server detects more than 8 cores per NUMA node, and it reserves the right to subdivide a NUMA node into smaller soft NUMA nodes to try to minimize the scheduling impact. If this feature is enabled, you can detect it in a number of different ways. The first is to check your SQL Server error log at the instance level startup. If automatic soft NUMA has been enabled, you'll see an error message as listed on the screen. You can also look at the DMV sys.dmos nodes for multiple node IDs with the same memory node ID. I'm not here to say that automatic soft NUMA will always be a bad feature. Many times it can help maintain performance while minimizing the impact of widely parallelized queries. However, I do find that in some cases it might catch you off guard. Imagine this scenario. You have 8 CPUs on a SQL Server reporting services reporting machine. It's running slow and taking a long time, so you add 2 cores to try to boost performance. You cross that 8 threshold and automatic soft NUMA enables itself. All of a sudden, your SQL Server report runs slower, and you find that only half the CPUs are being used. Automatic soft NUMA has kicked in and presented 2 NUMA nodes with 5 cores each, and your query could now just only have 5 cores available instead of the 8 that it had before. Monitor and review the platform to make sure that if this setting has enabled itself, it's not artificially slowing down your SQL Server workloads. You can forcefully enable or disable it with a trace flag at the instance level. Another completely random thing around CPU usage is to ensure that you have used the correct SQL Server ISO image for your installation. Enterprise and Enterprise Core are 2 different SKUs. Enterprise, but not Enterprise Core, has a 20 core max limit on addressable CPUs. I found a number of environments where the wrong ISO was used to do the installation and their SQL Server production machine was only able to use 20 of the available CPU cores on the service. If this is the case, you'll see an entry in the SQL Server instance error log at startup stating this artificial license limitation. You can perform a SKU update inside SQL Server quite easily, but it will result in about a 5-minute outage. Let's take a look at a couple memory-related settings now. Our instance level minimum and maximum server memory defines the amount of memory reserved for this SQL Server's buffer pool. First of all, make sure to leave enough headroom for your operating system and any background processes that are not contained in the SQL Server buffer pool or that originate from other software. It could be things like antivirus engines or security scanners, backup agents, or anything else your system administrators may have installed as part of central management of these servers. You might ask why I've set the minimum server memory here as well as the maximum for memory. Give me a couple slides and I'll show you. The next setting is the lock pages and memory setting. This setting allows your service account to not allow the Windows operating system to interfere or try to steal memory that you've instructed SQL Server to use for its buffer pool. You assign this under the local security policy, local policies, user rights assignment, and lock pages and memory setting. Restart your SQL Server service to allow this setting to take effect. I always want to make sure SQL Server has all the memory that it needs. Enabling this setting forces the operating system to not be able to try to reclaim memory from this instance. We have to be really careful here. The reason I told you to enable Reserve All Guest Memory for the virtual machine is that if Windows is being forced to give memory back to the hypervisor because of host-level memory pressure, enabling this setting here could get in the way of the balloon operation at the virtual machine layer. If there's the potential for host-level memory pressure and your virtual machine administrators will not allow you to lock all guest memory, I'd be a little hesitant to enable this setting just in case. Hopefully, though, enough memory exists at the host where you don't have to worry about this. Enabling this setting will allow us to enable large memory pages if you're running SQL Server Enterprise Edition. Large memory pages allows SQL Server to tell Windows to use a larger block size for its memory map for the SQL Server buffer pool. Trace flag 834 and having lock pages in memory set for the service account is the magic combination that tells Windows to increase its buffer pool block allocation size from 4 kilobytes to 2 megabytes. Think about how many pointers exist both in Windows and SQL Server for a buffer pool of 128 gigabytes if the block size is 4K. That's an incredible number of 4K pointers. Decreasing the number of pointers by increasing the block size to 2 megs makes SQL Server much more efficient. Making it more efficient means that we get a bigger performance gain. I generally look to enable this on enterprise SQL servers at or greater than 64 gigs of memory. Don't quote me on this, but I usually find that I get at least a 17% net performance gain in the entire SQL Server instance. You'll need to double check that you're not using column store indexes with large memory pages, as currently it's a known limitation within the SQL Server engine. These two features will not coexist. Explore and experiment with this setting. In virtual environments, enabling large memory pages will decrease something called a translation look-aside buffer, or TLB, miss. All the memory that's mapped to SQL Server in Windows must also be mapped at the hypervisor layer. Large memory blocks are fully supported inside VMware virtual machines, so if we can decrease the number of pointers that the virtual machine has to manage, we get an even better performance gain there. The more memory that SQL Server possesses, the better chance for a substantial performance improvement. As with anything, make sure you test to understand what your workload will do when this setting is enabled. You can double check that this is enabled with the query on the screen. If large memory pages have been successfully enabled, not only will you see an entry in the SQL Server error log at startup, but you'll see a large memory pages value when you run that DMV. Finally, these are shared everything environments. For highly intensive scheduled tasks such as backups, integrity checks, and index maintenance, not including things such as your nightly ETL or reports or anything else that you may have in your environment, I want you to try to stagger these operations the best that you can. Anything that we can do to not have these large operations running concurrently while on the same host will help the overall net performance of not only these, but the other virtual machines on the same hosts. I know it sounds like it's a lot of work, but if you map out not only the start times, but the expected end times of the individual major operations across your servers, you might find times of significant overlap. I found one environment with over 1,000 SQL servers where index optimizations was set to run nightly at 7 p.m. across all servers. For the next 2 hours, every machine ran incredibly slow and the storage performance took a dramatic hit while everything else was crushing the CPU in the sand. They had a 9-hour maintenance window each night to run these in. They didn't know any better, and they scheduled everything for the same time. We set varying schedules to start them on different 30-minute patterns over each evening, and everything was fine after that. Whew! At this point, your instance is ready for you to deploy and manage. Your CPUs have been aligned, your disks provisioned properly, your memory balanced with the instance and the host, and your jobs have been staggered appropriately. At this point, these should line up with the virtual machine layer much better than before. Your virtual machine density should improve and your performance should increase at the same time. Now it's time to dive into performance tuning in the next module for when things are not running perfectly. Whew! At this point, your instance is ready for you to deploy and manage. Your CPUs have been aligned, your disks provisioned properly, your memory balanced with the instance and the host, and your jobs have been staggered appropriately. At this point, these should line up with the virtual machine layer much better than before. Your virtual machine density should improve and your performance should increase at the same time. Now it's time to dive into performance tuning in the next module for when things are not running perfectly.